this video, we're going to look at a more complex Snell's law problem. So here's our scenario. Glass prism, 1.52 refractive index in a water trough, where light travels through the water and enters the prism perpendicular to the surface. Here's the diagram. So we've got a glass prism. There we go. Here's our light coming in perpendicular. The prism has an angle of 45 degrees and 90 degrees. There we go. Alright, let's look at the questions. So with this diagram, the first question asks, explain why the incident ray angle is undeviated as it enters the prism. The second question is, what is the angle of incidence as the ray hits the far side of the prism? And finally, question C asks us to calculate, using Snell's law, the refractive angle as the light ray emerges from the glass prism, noting that water has a refractive index of 1.33. So let's look at a solution for A. Okay, so let's revisit the question. Explain why the incident ray angle is undeviated as it enters the prism. Now the incident ray basically hits at 90 degrees, at the boundary at 90 degrees from the water. Now at 90 degrees, as you can see as it comes in here, okay, the speed is going to change, but because the angle, it's not coming in at an angle, the angle will not change at all. So anything hitting at 90 degrees will pass straight through the block. Now we've seen this in some of our practicals that we've looked at. Okay, so let's look at solution B. Now the solution to B, or the question asks, what is the angle of incidence as the ray hits the far side of the prism? Well, we know the angle of one is 45 degrees, which means the other one must be 45 degrees. It's an equilateral triangle. That means the equilateral triangle is also made between the incident ray coming in. Now here's the normal, which means if it's 45 degrees on one side, it's going to be 45 degrees on the other, because it's got to be 90 degrees overall. So as a result, that means that the incident ray is going to be hitting the far side of the prism at an angle of 45 degrees to the normal. Okay, so we now know the incident ray, which is going to be helpful to solution C. Okay, so let's look at the question. We're going to use Snell's law to calculate the refractive angle of the ray as it comes out of the glass prism, noting that the water's refractive index is 1.33. The glass prism is 1.52. So let's put down what we know. We know the water's refractive index is 1.33. The refractive index of the glass is going to be 1.52. We've also calculated that the incident angle where it leaves the glass prism is 45 degrees, and we're working the refractive angle as it enters the water. Now note we've swapped over, so we're going to use Snell's law with n1 sine theta 1, which is going to be the glass, equals n2 sine theta 2. So let's draw a diagram to represent this. So here's the far side of the prism, here's the normal that we've drawn in, here's our incident ray coming through the glass, and here's our refractive ray coming out. Now remember, the refractive ray theta 2 has got to go to the normal, so we've got glass on the left and water on the right this time. Alright, so let's substitute this into our equation for Snell's law. n1 sine theta 1 is going to be the glass, n2 sine theta 2 is going to be the water. So n1 is going to be 1.52 sine 45. On the other side, I've got 1.33 refractive index of water. Now I take the 1.33 to the other side to give me sine theta 2. That's all good. Take it up to the other side, and as I solve this, I know that sine theta 2 is going to equal 0.81. Then I do the inverse sine of 0.81, which is going to give me 53.9, which I can round up to 54 degrees. Okay, so sine theta 2, as we know, is now going to be bigger than theta 1 as the speed increases as it enters the water, because the water is less dense than the glass. Okay, thanks for watching.